Okay, 2.5, day 2. Welcome back. Okay, we're picking back up here on example 9. All right, we're going to have to use what's called this linear factorization theorem. It's really just an extension of the fundamental theorem of algebra. Okay, remember, fundamental theorem of algebra is very fundamental. It just says that if I have a second degree function, if I include complex numbers and whole numbers and things like that, then it has 2 zeros. This one has 3. This one has 4. Okay, if we consider the complex number system. All right, and so now you take those zeros and you can just make linear factors of those. So whatever if it's fourth degree, you might have 4 zeros, and we just subtract them from x, and we've got what's called the linear factorization theorem. Okay, so if it's degree 5, then we know we could come up with 5 linear factors. Okay. Okay, and we've discussed this a little bit too, but here's the official statement. Anytime you have a complex number, 2 plus 3i or something like that, then its conjugate, a minus bi, is also a 0. We've used the phrase conjugate with dividing zeros in section 2.4. All right, so they always come in conjugate pairs every single time. Okay, even on number 76, your last OTI problem, your last 2 zeros were like, I'm just making this up, can't remember, maybe like 6 plus 1/2 I, and it was 6 minus 1/2 I. Okay, so if a polynomial function with real coefficients has these given zeros, okay, let's write the polynomial function. And we did one like this in section 2.2 as well, but now they just weren't, imaginary numbers. Now they are. Okay, so if we know 3i is a 0, we got to realize that its conjugate is also a 0. It must be. Okay, so 3i. So if I write that as in the form a plus bi, it's 0 plus 3i. So its conjugate then is 0 minus 3i, simply put. Okay, so negative 3i must be a 0. All right, we're always going to be able to assume that. Same thing down here. Figure out that conjugate. It must be a 0. Okay, and I'll just point up here. Must be a 0 because of this theorem up here. Okay, so here we go. We can build our function now by using the linear factorization theorem. If we know the zeros, we can use that factor theorem. So we say x minus c, or k. So x minus that 0 is going to be x plus 1. Continue building this function, x minus 3i, and then x minus a negative 3i. All right, there it is. They usually want you to multiply this out. All right, because right now it's in factored form. So to multiply this out, I could start by multiplying these two together, but it's going to make the process much easier if you start by multiplying the factors that have the imaginary ones, okay? Because they'll end up simplifying right out of the problem. The imaginary parts will, if you're doing it right. All right, so I'm going to do x times x, positive. Now I have 2 variables. Doesn't really matter what order you write it in. Typically, we write the 3i first, then x, but it doesn't matter. This I get negative 3ix. And here I'm going to get negative 9i squared. Okay, so the middle terms are opposites, so that gives me 0. Now remember, whenever we see I squared, you're expected to replace it with negative 1. So I have a minus 9 and a negative 1, so that gives me positive 9. Okay, so as you can see now, if we multiply those two together, usually the i's will disappear or simplify out. All right, so now I need to bring the x plus 1 back into play and multiply these two. Okay, so I get x cubed, 9x, 1x squared, and positive 9. Okay, and then just kind of rearrange it and put it in standard form. So we have x cubed plus x squared plus 9x plus 9. Now, it does say there are many correct answers. Remember back in section, I can't remember if it's 2.2 or 2.3, I said you could multiply this by any a value, any coefficient, and we still get the same zeros. So that's why there are many correct answers, but just leave it like that, okay? All right, time for you to try it. I want you to pause, figure out this conjugate, set it up and multiply, and then see what you get, okay? Go ahead. Okay, here's your feedback on 10. 5i must be a 0 due to the complex, the conjugate pair theorem. All right, so then I multiply those together. This is what we get. We get x squared plus 25. Multiply that by x minus 3. Here's your final result. Okay, pause and correct if you need to. Okay, we're going to skip numbers 11, 12, and 13 this year. We're going to keep that example pretty simple. Okay, we're going to wrap it up here with Descartes' rule of signs. All right, Descartes' rule of signs. That's named after René Descartes, a French mathematician. All right, now what this does kind of has a goofy explanation, but once you see it in action, I think things will click. Okay, it's a way to narrow down the number of positive real zeros and also the number of negative real zeros. So if the real zeros, they actually have x-intercepts. Okay, if they're complex numbers, 8 plus 6i, then it actually doesn't have a x-intercept with it. But let's just say we have a function that's doing a bunch of turns and it looks like this, okay? What this is going to do is narrow down these possibilities, the number of them. So here I have 3 positive zeros and here I have 2 negative real zeros. This gives us the possible number of them, okay? All right, so let's start off with finding the positive real zeros. There's basically 2 tasks to each of these. I got to figure out the positive and the negative, okay? So to find the positive real zeros, all we have to do is count the number of variations in the sign. I'm going to label this here positive real zeros, and over here we'll do the negative real zeros, okay? So positive real zeros. So the number of sign changes, right now it's positive, and now it's going to go to negative. So we call that a sign variation. I'm going to go ahead and just create a running tally down here. Encourage you to do the same thing. All right, now from here it goes from -2 to +5. That's another sign change. So now we're up to 2 sign changes. Okay, and then we go from 5 to 7. So now we're up to 3 sign changes. All right. Okay, so here's what you do. You take those number of sign changes and you just subtract 2 from it. So we say if there's 3 or 1 positive zeros. Okay. Okay, you might be wondering, all right, where did he get the 1 from? This is where this is a little sophisticated and they explain this kind of confusing at times. But I take the number of sign changes or less than that number by an even integer. So I subtracted 2. Why didn't I subtract 4 or some other even integer? Because that'd be a negative. 3 take away 4 or 6, I'm at a negative number. It doesn't make sense for a quantity of zeros. All right, basically the trick is whatever number you get for the sign changes, you just subtract 2 till you can't anymore. So for example, let's just say I went through here and I had a really big function and I got 7. So if I got 7 sign changes, I'd say 7, 5, 3, or 1. Okay, just keep subtracting 2 until you get to basically 0 will be our cutoff. Okay, because we can't have a negative quantity of zeros. All right, so if you use that trick, even if it's an even number, I'd say 6, 4, 2, or 0, and stop at 0. All right, so let's move on to negative real zeros. Okay, for negative real zeros, we're actually going to count the sign changes again, but we have to use f of negative x. So that's something worth making sure it stands out. That's what makes a difference. And then the process is the same. So we have to evaluate this function with negative x first. So write this down. Okay, and then we got to simplify this. Slow down, make sure you do this right. Exponents first, so -1 to the third power is -1. All right, so I end up with -x cubed here. I'm going to make this a two-step process because it's important. Students mess this up all the time. So -x to the third is -x cubed. Okay, and here's the biggest mistake right here. Students see the minus negative and they can't resist. They write the +2. Stop, slow down, do your order. We should be taking care of this first. -x times -x is positive x squared. Okay, I didn't do anything with the -2 yet. All right, so as you can see, we're ending up with -2x squared, not positive 2x squared. Do your exponents first. All right, here the exponent is just 1, so nothing to do here. So if we want to go ahead and do -1 times 5, we can now. All right, so here's the final expression for plugging in -x. -1 now times the 4. Positive times negative, so we get -2x squared. Okay, so I have no sign changes. This stays from negative to negative all the way through. So if it has no sign changes, we say there's no negative real zeros. So there's no, or 0, if you want to write the word 0, it's fine. No negative real zeros. Okay, it's a little goofy. I probably need to show you too. So let me take you through 15 and then you'll try 16, okay? All right, so remember the positive real zeros, we can just use the original function right now. I'm gonna go a little bit quicker this time, okay? All right, so what do we have? There's no sign change there. The first one is right here, so I'm at 1. Okay, and then it goes from positive to negative, so now I'm at 2. Okay, so all I do is say whatever that quantity of zeros is, 2. Now I subtract 2 from that. 0, I'd continue to subtract 2 if it made sense, but it doesn't. So I say 2 or 0, positive real zeros. Okay, I should have said real up here too, because we got the real zeros and the complex zeros. All right, that's it for that one. So negative real zeros now. Let's evaluate the function with -x. Okay, be careful with this one. I've got a negative out front, so I have a negative. Now I plug in the -x like this. Okay, pause if I'm going too fast. I'm going to keep going here. So -x cubed is -x cubed. All right, and now negative times negative. So I get positive x cubed here. This one is positive x squared. Now multiply it by -5. Okay, now this one's -8x, and that's -9. All right, count the sign changes. Here I'm at 1, and that's it. I only had one sign change. Okay, so here I'm going to say 1 negative real 0. Can't subtract 2 because I'm going to be at -1. So we just stop there. Okay, your turn. Try 16, and then we'll see how you do. Okay, hopefully it went good. 4 total sign changes, so we just keep subtracting 2 till we can't anymore. 4, 2, or 0, positive real zeros. Okay, check your simplifying for this one. Everything worked out to be positive, so there are no negative real zeros. Okay, that wraps up 2.5. We'll see you soon.